Okay, so let's check if this theorem is true. Of course it's true, but so the set S must be connected and compact. So for example, the banana example is a good one, because the triangle with the 3 points here is not good, because the 3 points do not form a connected set, but the banana is a bounded, closed, bounded, and connected set. So suppose that we have this banana, okay, and let's construct the convex hull. Qualitatively is going to be basically something like this. Right? I'm not very precise, but you can imagine. So it's going to be the smallest convex set that contains the banana. And now the theorem says that every point in the convex hull should be given, can be expressed as the convex combination of at most 2 points in the original set. So here we have the original set is S. Let's write S. Here is the banana. The convex hull blue is R. Now what happens? If the point we want to represent is a point of S, that's obvious, right? Any point here is represented as a convex combination of itself with anything else, because you just put coefficient 1 to this point, so you have it. So it remains to be seen what happens to points that are not in S, but they are in R, in the convex hull. And the theorem says that any point in the convex hull can be written as the convex combination of 2 points in S. Why 2? Because here D is equal to 2. We are in the 2-dimensional space. And in fact, if I take this point, for example, well, I can pick a segment passing through this point and joining a point here and a point here. Those points are in S, right? So, and the blue point is clearly given as the convex combination of these 2 red points. Of course, this is not a unique choice. I could have picked other 2 points. So it's not a unique representation, right? But the theorem says you can do it. You can represent any point in the convex hull as the convex combination of at most D, in this case D is equal to 2, points of the original set. That's an important result that will be used in a certain results in information theory. So we put it here and use it later. Now, having seen convex sets, now we can introduce the concept of convex functions. So let's consider functions from Rd to R. A function from Rd to R. Now I want to add a page because all these things are easier when I introduce some oh, okay, the paper is already there. Good. Okay, so for example, let's consider a function g from R2 to R. So this, where we have R2, say the plane xy. This is R2, is this plane. And the function will be, some sort of surfaces like this. With, okay. Of course, it could be, this very strange function that does whatever. So we define something called the epigraph, denoted as AP of G, as the set of all points given by x as an argument of the function, and a is like the a sort of level that cuts the function horizontally. So we consider all the points in the level set. So in other words, imagine that we cut this function here. Oh, now I'm going to do it. It's going to be at a certain with a plane at height. I use a different color at height a. Okay, so this is a. So this is going to cut a level set here. Those are all the x's for which g of x, this surface is g of x, is less than a. And then I take the points of coordinate x and a, and I get basically this thing. Okay? And in fact, I get all the points below level A. Okay? So you see it from here. XA for all the x's less than A. So basically, okay, this is a bit, I should have done it maybe not in 3 dimensions, in 2 dimensions would have been simpler. So let's do it in 2 dimensions. If I have 2 dimensions, then I have the function, maybe this is my function g, and then I cut it with the level a, right? And then I see the epigraph is going to be basically the set supported by the function and the level. Okay? And then you do this for every a, and so at the end you're going to have basically all the supported set, all the things, the area above the function g. Okay? So we say that g is a convex function if AP of g is a convex set. So in other words, for example, in my plot here, this g will not be a convex function. Why? Because this red set here is non-convex. For example, I can take a point here, and oops, the convex combination is not in the set. But for example, a sort of parabola would be convex, because a parabola is like this. The epigraph is this set, and this is a convex set. So, for example, a quadratic curve with a concavity upward is convex. An exponential is convex. The exponential is a convex function because the epigraph is convex. There are plenty of functions that are convex. Okay, and in simpler terms, we can say that for convex functions, for any argument x and y in the domain, the convex combination alpha gx plus 1 minus alpha gy is greater or equal than the function of the convex combination of g of alpha x plus 1 minus alpha y. You see it immediately in a plot like this. Let me do another qualitative plot. add page. So let's consider a convex function. Let's do it in 2 dimensions because I tried in 3 dimensions, but it was a mess. So we have, for example, a sort of parabola like this. This is convex, this is the epigraph, right? So let's take 2 points. I mark them in blue. X and Y. Say Y here, not Y here. Okay. So, and the corresponding G of X and G of Y. And now consider a point in the convex combination. So I consider a point here, alpha x plus 1 minus alpha y. This is simply any point in the joining segment. So I pick a point in the middle here, but it could be any point in the segment. And the corresponding G of, let's call this point Z. This will be G of Z, right? And now let's consider the convex combination with the same alpha of G of X and G of Y. The convex combination is basically something that is obtained by taking the straight line to the chord joining these points, and it will be a point around here. And this point, this convex combination, will be always above this. So you have that alpha G of X plus 1 minus alpha G of Y is greater or equal than G of alpha X plus 1 minus alpha Y. Okay? This is the fundamental property of convex functions that says basically that the convex combination of the function is greater or equal of the function of the convex combination. Greater or equal than the function of the convex combination. Okay? So in terms of names, well, when the function g is convex, then it's negate when we multiply by -1. Of course, everything is flipped upside down. We call it concave. And for concave functions, of course, because it's a minus, this relation is reversed. So for concave functions, the convex combination of the function is less or equal than the function of the convex combination. And it turns out that there is also an analytical property. When g is twice differentiable, so when the second order partial derivatives exist, then the function is convex if it's Hessian. The Hessian is the matrix of second partial derivatives is positive definite or positive. What does it mean, positive definite? Oh my goodness. Review your linear algebra. Positive definite, a matrix is called positive definite. So a matrix A is positive definite if for every vector x, x transpose A x is greater or equal than 0. Okay? Now, it's called strictly positive definite if this is true for strictly positive for any x non-zero. Of course, when x is the 0 vector, this thing is 0. When there are non-zero vectors x for which this quadratic form is 0, then the matrix is called positive semi-definite, or like, okay, so distinguish between strictly positive definite and positive semi-definite, but okay, this is the meaning of positive definite. And if you remember a little bit about your notion in geometry, when we look at so-called paraboloids, well, the paraboloids have a quadratic term of this form, and when the matrix is positive definite, then effectively the paraboloid is like this with concavity upwards, which is precisely a convex function. When the quadratic surface has the matrix here is non-positive definite, then it may not be a parabola. There may be some other curve. Okay, so you have these things to remember. But okay, so in other words, how do I check if a function is convex? Well, if it is differentiable twice, then I look at the Hessian matrix, so the matrix of its second derivatives, and then I study it and I see if it is positive definite. Otherwise, well, it's a good question. Proving convexity is generally not super easy, but once we know that the function is convex or concave, then we can use this fundamental property that there is these inequalities that relates the function of a convex combination with a convex combination of a function. And this is useful to get bounds, and in particular, this property stated in terms of expectation is the famous Jensen's inequality, which we will use a few times in this course. Jensen's inequality says the following. It says that if G is a convex function in Rn, and we denote by Xn a random n sequence with, say, real valued, then the expectation of G of Xn is greater or equal than G of the expectation of X. So expectation is a little bit like a convex combination because it's a sum with weights that sum to 1, which are probabilities of particular values, which are the particular determination of the random sequence Xn. So you see that this is exactly the same property said before, but in more general terms. And of course, for concave functions, for what I said, the equality is reversed. So if G is concave, then the expectation of G of X is less or equal than G of the expectation of X. So this is Jensen's inequality. And now we simply use Jensen's inequality to prove the information inequality, which is basically the result that says that for any two distributions, P and Q on a common alphabet X, the divergence P of P and Q is greater or equal than 0. As I said before, this is a very, very fundamental inequality that, in fact, somehow generates all other inequalities of, say, the classical information theory, called Shannon type inequalities. And it says also that this is true, say that E is 0 if and only if P and Q coincide. So how do we prove this? Well, we write minus the divergence. Well, first we define the alphabet, the subset A of all the points in X such that P is strictly positive, because we don't want to divide by 0, right? So then remember that how the divergence is defined. The divergence is defined in general, let me write it here as a reminder, D of P and Q. I will neglect the subscript X because otherwise it's too heavy to write, is sum over X in alphabet X of P of X log P of X Q of X. Okay? But now we see that for all the x's for which p of x is 0, this term, this contribution is 0, because we have essentially 0 times log of 0. Now, log of 0 is technically minus infinity, but we regularize these terms because this is, imagine that this is something that goes to 0, then when p of x is like epsilon, almost 0, you see that the linear term here wins against the logarithmic term, and so the limit is 0. So when for some x's p is 0, the term p log p is also 0, okay? And which means that this sum can be restricted to the terms in A, because all the terms that are not in A have p of x equal to 0 and do not contribute to the sum, okay? So once you have this, now you see that now when we restrict to this set, all these p's are positive. So now we can write minus the divergence in this way, because now we are dividing by these p's, but they are all strictly positive. So we are not dividing by 0, okay? So now what we can do is use Jensen's inequality. This can be seen as the expectation of the function log of q over p, but logarithm, guess what? Logarithm has this graph. This is the point 1 and 0. Logarithm is concave because minus logarithm is convex. So we use Jensen's inequality that's for concave functions that say that the expectation of the function is less or equal of the function of the expectation, which means that bringing this sum inside the logarithm, we get an upper bound. But now p and p simplify. So this is logarithm of the sum over set A of q. But q is a probability mass function. When we sum over all the alphabet, we get 1. And it's clearly an upper bound because logarithm is an increasing function. If we add more terms in the sum, more non-negative terms in the sum, we get an upper bound. But this is equal to 1, so log of 1 is 0. So we have proved that minus divergence is less or equal than 0, or if you want, divergence is greater or equal than 0. Okay? And yeah, so this is the result. So what are the immediate consequences of this result? Well, first of all, since the mutual information is a divergence, then the mutual information is always greater or equal than 0. The conditional mutual information is always greater or equal than 0. And because we can write the mutual information as the entropy of one variable minus the conditional entropy of that variable condition on the other one, and this is greater or equal than 0, we find that the unconditional entropy is always greater or equal than the conditional entropy. Or if you want, we find a fundamental thing to remember: conditioning reduces entropy, which makes perfect sense because entropy in a certain sense is a measure of randomness. The more random this something is, the largest entropy. Now when we condition on something else, so we give like a sort of extra condition, we are like reducing the randomness because we are conditioning, and conditioning reduces entropy, which makes also intuitively perfect sense. So other immediate consequences are that the uniform probability mass function over an alphabet maximizes the entropy. How do we see this? Well, we see it from simply by computing the divergence between a uniform distribution and any given distribution. If I compute d of px U, where U is, say, ux. Ux is the uniform distribution over x. So what is this? Well, this will be, by definition, is sum over x, p sub x, log p sub x. And then the uniform distribution is simply 1 over the cardinality of the alphabet, but this is simply log of the cardinality of the alphabet, and then minus the entropy of x. Now, how do I do this? Well, use the logarithm, expand this, sum everything, and find the result. So you have to be complete. Go from here to here. You do it. So, but this is divergent, so this is greater than or equal than 0, and therefore we see that the entropy is always less or equal than logarithm of the alphabet, which is the entropy of this uniform distribution. Logarithm of the alphabet is the entropy of the uniform distribution. Another consequence is the fact that so-called independence upper bound on the joint entropy, because we can use the chain rule from here. Use the chain rule. We write the joint entropy using the chain rule is sum from 1 to n of the entropy of xi given entropy of the sequence from 1 to I minus 1. But we know that conditioning reduces entropy. So what happens if I eliminate this conditioning? If I eliminate the conditioning, I increase each term in the sum. So this will become less or equal, because I'm increasing each of these terms, of simply the unconditional entropies of the elements. So we see that the joint entropy is always less or equal than the sum of the individual entropies. Which is these inequalities in this theorem. So there are more convexity properties of divergence and entropies and mutual informations seen as the functions of the corresponding probability vectors and probability matrices. I will devote this to problems. You will find more details in problem sets with solutions, because this is a bit tedious analytically. You have to check typically calculating Hessian matrices and checking that they are positive definite. So I will pass through, and I would like to conclude with two very important inequalities. These are the first big information theoretic inequalities that we will use many times in the course. They're very important. One is the so-called data processing inequality. So the data processing inequality says the following: if we have three random variables x, y, and z, and they form a Markov chain, and I use this symbol, this means x, y, z, they are such that the joint distribution pxyz factors as px, py given x, pz given y. Notice that this is a special case. The general telescopic property would say pxyz factors in px, py given x, pz given xy. Okay? But as a special case, we have the Markov chain. When these variables x, y, z form a Markov chain in this order, then the conditioning is always just to the immediate previous variable. Here, for example, the conditioning of z, when you condition on y, the condition on x disappears. So then we have this. Okay? Then we have so this is a special property. Not all three random variables form a Markov chain. They would normally obey this general rule. okay? But if the three random variables form a Markov chain in this order, then it turns out that the mutual information between the extremes, x and z, is always less or equal than the mutual information between either x and y or y and z. So we have these two inequalities. And this is very easy to prove. It's just an application of the chain rule. It's an application of the chain rule because what you can do is to expand the conditional mutual information of x and y on one hand. Sorry, it's not conditional. I take it back. Expand the mutual information of yx and z using the chain rule. I use you see, this is a vector of two components. This is a scalar, so I can expand this in the order x, y. So I use the chain rule, and I get here the mutual information of the first component x and z, and the mutual information of the second component y and z given the first x. Or I do the expansion in the direction y x, and so I have the first here and the second given the first here, right? And then we can notice, for example, that here, because of the Markov chain, a property of the Markov chain, remember, is that when you condition it with respect to the middle variable, the two extreme variable becomes conditionally independent. So this means that the mutual information of x and z, which are the extreme variables, condition on y is 0. So this term is 0. So it means that this mutual information is equal to this mutual information plus something that generally is greater or equal than 0, which automatically implies that y mutual information of y and z is greater or equal to the mutual information of x and z. Okay? In this way, you have proved, for example, this inequality. And by taking another expansion, you do it yourself, complete the proof. You can prove also the second inequality. Now, let me just comment why this is called the data processing inequality, because it may not be completely obvious. So, data processing, why is that? Imagine that we have some source that produces x. X is a random variable. It could be a random sequence, whatever it is, right? And then this goes through a sensor that gives us a measurement, y. So this is like the raw measurements, what we get from the sensor, so the raw data. And then we say, oh, now we have to process this data and extract, extract information. Okay, so we put this into a computer, and this gives us something else called z. Maybe these are, who knows, the measurements we get from a sensor, and here this is, for example, this is like the output of the radar antenna, and this is a radar detector, and this is the information that we actually see on the screen. Okay. Well, the theorem says one thing. It says that you cannot manufacture information. Basically, it says that the mutual information from here to here is always greater or equal than the mutual information from here to here. So all what you can do, all what this computer can do, is to extract the information that is already present in the measurements. It cannot add anything else. Okay? And this is a property of the fact that x, y, and z form a Markov chain, because It means that, you know, all what we convey on X to Z has to go through this sort of bottleneck Y. In fact, the Markov chain property says that if we condition on this two becomes independent. Okay? So this is to say, whatever clever machine learning post-processing of data you can do, the best you can do is to extract the information that is already present in your measurements, in your data. You cannot manufacture new information unless there is some other ways, some side information coming from other paths. If the path goes through this measurement, so we have this Markov chain structure, then we have this inequality. Okay, that's why this is called the data processing inequality. The other inequality is called Fano inequality, from the name of a professor at MIT at Shannon's time who found this inequality. It's a very, very beautiful result, very simple result that relates information theoretic quantities, like in this case conditional entropy, to the probability of error in making a decision. Okay, and this is really fundamental when we will prove results on coding, on channel coding. Okay, so the final inequality says the following: suppose that I have two random variables, x and y, x and x hat, and basically with a certain joint distribution. Okay, and our goal is to guess the value of x from the value of x hat. So imagine that the x and x hat take on values on the same alphabet, and basically x hat is the output of a detector, of a decision-making algorithm. Okay, so we define the probability of error as the probability that the algorithm does wrong, so that x is different from x hat. X hat is the answer, x is what we want to guess. When they are different, it's an error. Okay, and the probability of this of x different from x hat is the probability of error. And the final inequality says that the conditional entropy of x given x hat is upper bounded by the binary entropy function calculated in the probability of error times the probability of error itself times the logarithm of the alphabet of possibilities, the alphabet in which x and x hat take on values. Okay, and now since we know from before that the binary entropy function is always upper bounded by 1 bit, then we can also relax this bound and make it a bit simpler and say less or equal than 1 plus probability of error times logarithm of the alphabet. How do we prove final inequality? Here is the proof. So we define a random variable E as the indicator of the error. So 1 of a set is the indicator function of the set. So you see this notation here, 1 of x, 1 of x different from x set. This is a symbol that says this is 1 when they are different, 0 when they are equal. Okay, so this is a new binary Bernoulli random variable that has probability of being 1 is precisely PE, the probability that x is different from x hat, and the probability of being 0 is 1 minus PE. Okay, and now we write the following. We write the conditional entropy of x ne given x hat, and we use the chain rule in two different ways. We expand in the vector x comma e in the order x e, so we get the entropy of x given x hat plus the entropy of e given x and x hat. We expand this in the other order, e first, so the entropy of e given x hat, and then the entropy of x given e and x hat. And now we have to reason and notice that first, the entropy of E given x and x hat is 0. Why? Because E is a function of x and x hat. So if you condition on x and x hat, E becomes the deterministic quantity, and any deterministic quantity has 0 entropy, because the probability mass function would be simply a vector of all zeros and a single one at the value, or at the deterministic value that of that quantity. And now you see that the entropy is going to be 0, because you have all 0 times log that gives 0, and 1 is 1 times log of 1, and log of 1 is also 0. So any deterministic quantity, or any quantity that is deterministic after conditioning, the corresponding conditional entropy is 0. So this is 0. On the other hand, let's look at the other two. So here you see we have this term, which is the first, is this one, right? And now we want to upper bound these two terms, and then we get the upper bound. So let's consider first the first term, so the entropy of E given x hat. Well, we know that conditioning reduces entropy, so removing the conditioning gives you an upper bound. If we remove the conditioning, we get just the entropy of E. But the entropy of E is the entropy of a Bernoulli binary random variable, so it's the binary entropy function calculated in P. So we have this first term. Now let's consider the second term. This is the entropy of x given E and x hat. Now we can expand this conditional entropy with respect to E, because we can compute the conditional entropy for fixed value E equal to 1 and equal to 0, and sum with the probabilities. So what happens here? It happens that for the second term, when E equal to 0, x is equal to x hat. So this term is 0, because this whole term is 0, because conditional equal to 0, then x becomes a function of x hat, and therefore is uniquely determined by x hat. And for the same reason I said before, that the conditional entropy of something that becomes deterministic given the conditioning is 0. And this other term here, let's see, P is here, and this is simply the entropy of x given something. Now this condition is complicated, but then I can use the trivial upper bound that we saw before. The entropy, first of all, I remove the conditioning and I get an upper bound. Second, I don't want something that depends on x, so I simply take the log of cardinality of the alphabet. So I get this upper bound here. So I put now this upper bound together with this upper bound in the second line, and I get exactly this expression, and the final inequality is proved. So why final inequality is important, we will see pretty later in the course, that we want to somehow lower bound the probability of error on any hypothetical decision-making system. Well, we have this lower bound right here, because we can write return this inequality as PE greater or equal, and then we are going to have entropy like this, minus 1 divided by log of the alphabet. And it means that we can find lower bounds, so best possible cases to the probability of error by studying these information theoretic quantities rather than analyzing the specific decision-making algorithm. Okay, so these will be instrumental in finding something that is called the converse results to the, for example, the channel coding theorem, that is an inexistence proof. Basically, we will prove that there is no coding system that achieves low error probability when transmitting at rate above capacity, and the final inequality will be the fundamental tool to prove these converses. Okay, so this is the end of chapter 1. Admittedly, it's a lot of material. So you are supposed to go to the material, try to complete the proofs that I left open, try to understand, and in the first live lecture we will, so in the first week, we will go through some examples, some exercises, and of course through your questions. So please come to the live Zoom lectures, because it's the only opportunity we have to interact.